Hello and welcome. Today, we are diving deep into a topic that is, let's be honest, seriously mind-bending. But it's also a science that's hiding in plain sight, powering just about everything you use. We're going to be decoding the quantum world. Okay, so here's the game plan. We'll start with the tech you know and love, then we'll see where the old physics started to break down, uncover the universe's strange new rules, connect all that weirdness to real-world tech, and finally, take a peek at what's coming next. So let's start with something you probably have with you right now, the incredible quantum machine hiding right there in your pocket. And no, that is not an exaggeration. I mean, the device you're watching this on right this second, the microchips buzzing away inside it, the lasers that shoot data across the oceans, none of it, and I mean none of it would even be possible without our grasp of the quantum realm. It's the bedrock of our modern world. Which, of course, brings up a huge question, right? How in the world did we get from these bizarre abstract theories about tiny invisible particles to the powerful gadgets that basically run our lives? Well, to answer that, we've got to rewind the clock to a time when our whole common sense view of the universe just started to completely unravel. For centuries, we really thought we had the universe figured out. But right around the turn of the 20th century, as scientists started peering into the super tiny, they found some serious cracks in everything they thought they knew. For the longest time, all we needed was classical physics. You know, Isaac Newton stuff. And it's amazing for predicting the path of a planet or how a baseball flies through the air. It's intuitive, it makes sense. But when scientists tried to use those exact same rules on atoms and electrons, the math didn't just get a little wrong, it just broke completely. And that was a huge deal, because it meant there had to be an entirely different rule book for the tiny stuff. And what followed was a flat-out revolution. It was this incredible cascade of discoveries. First, Max Planck figures out that energy isn't smooth. It comes in little packets he called quanta. Then a young Albert Einstein comes along and says, hey, what if light itself is made of these packets? And then Niels Bohr took that idea and applied it to the atom itself. Each discovery was like opening a door into a new reality, one that was a whole lot stranger than anyone had ever imagined. And this brings us right to the core of it all, these new, strange rules that the universe actually plays by. And I'll give you a heads up. This is where things start to get wonderfully weird. So the first strange rule is something called wave-particle duality. Basically, if you ask whether a tiny thing like an electron is a wave or a particle, the universe's answer is yes. It can act like a spread-out wave in one moment, and then like a tiny, localized little ball the next. And get this isn't some quirky theory. It's a proven fact. An experiment called the double-slit experiment, probably one of the most famous experiments in all of science, proved it beyond a doubt. It showed the particles act like waves when you're not looking, but the instant you try to measure them, they snap into a single spot like a particle. It's almost as if reality itself waits for us to look before it makes up its mind. This weirdness led the physicist Werner Heisenberg to a staggering conclusion we now call the uncertainty principle. It's a fundamental cosmic limit. It means you can never, ever know everything about a particle all at once. The more precisely you nail down its location, the fuzzier its speed and direction become, and vice versa. A good way to think about it is to picture a fan spinning really fast. You can see the blurred circle where the blades are, you know its general location, but you can't possibly tell me the exact position of any single blade. Now, if you stop the fan, you know exactly where the blades are, but they have zero momentum. See? It's a trade-off that's just baked into the fabric of reality itself. And oh, the weirdness just keeps on coming. Next up is superposition. This means a particle can literally be in all of its possible states at the exact same time, until you measure it. And then there's entanglement. This is where two particles can become so deeply connected that what happens to one instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy. This was so bizarre, so counterintuitive, that even the great Albert Einstein had a huge problem with it. He famously called it spooky action at a distance, because it seemed to break the cosmic speed limit, that nothing can travel faster than light. But here's the kicker. Experiment after experiment has proven that this spooky action is absolutely real. Okay, so we've got all these bizarre, spooky, mind-bending rules. You might be asking, so what? What's the point? Well, this is the payoff. This is where we see how humanity learned to put all that spookiness to work. You see, every single one of those strange rules has a powerful real-world application. Remember Niels Bohr's idea about electron energy levels? Boom, that's how we get lasers and LEDs. Einstein's discovery about light acting like particles? That's the core principle behind every single solar panel. Heck, even MRI machines in hospitals are quantum technology. They work by manipulating the quantum spin of atoms inside your body. But the real heavy hitter, the engine of our modern world, is the microchip. Our ability to perfectly control the quantum behavior of electrons moving through silicon is what makes all of our computers possible. Think about this. Over 90% of the new microchips that power the entire global economy simply would not function without quantum mechanics. So that's where we are today. But where do we go from here? We harnessed that first quantum revolution to build our digital age. And right now, a second quantum revolution is just getting started. This next wave of technology is going to use those even stranger rules, like superposition and entanglement, much more directly. We're talking about developing quantum computers that could solve problems that would take today's best supercomputers billions of years. We're talking about creating encryption that is physically, fundamentally impossible to break. This isn't science fiction anymore. It's the next frontier. And that leaves us with this one last big idea to chew on. That first wave of understanding quantum mechanics gave us computers, the internet, and the entire world we know today. Now that we're starting to really control the weirdest parts of it, what kind of world are we going to build next? The future isn't just coming, it's quantum.